Hello there. So this is going to be a crash course, and I mean seriously a crash course on abstract algebra. I should have written that. But, and we're going to be talking about fields, rings, groups. Now, before you run away, you already know some fields. The real numbers are a field. The rational numbers are a field. I'll explain what rational numbers are. I suspect a lot of the audience already knows, but just in case, we have the complex numbers as a field, and yeah, those are examples of fields. Abstract algebra. Okay, so these are fields. It's very messy today. I'm sorry. What makes this special is, well, you have let's do it in this order. Plus, you have addition, subtraction, multiplication, and division. Then we'll talk about rings and groups in more detail, really quick, like super crash course here, okay? Rings, you basically remove the division there, so you have plus, minus, and times. And groups, I'm just going to say groups are very general. You have some kind of operation, some kind of binary operation. It could be plus. And I'll put in parentheses over here because the minus and the division are basically the inverses of addition and multiplication, right? So, yeah, I think that makes sense to a lot of people, but maybe some people are like, what? So I guess I'll explain that a little more. So, in addition, you add some numbers, right? So we have, let's be concrete instead of using variables. Let's say 5 plus 7. So the number 7 can be added. So this is an element of the field. So all of these, you start with a set. You start with a set, and that's just a collection of objects, essentially. And we don't have to talk about numbers per se, but let's like kind of be grounded in normal human kind of math and just say we're talking about numbers. And so the number 7 can be added. That's an element of the set, so it's an element of our field. Let's talk about fields for now, okay? And so what would be the opposite of adding 7 would be to subtract 7. And so what do I mean by the opposite, or I should say inverse? The additive inverse means that when you have plus 7, and the additive inverse is the thing that gets you, in this case, 0. But 0 is the additive identity. So we're using a lot of special language to really just say things that you probably already know, right? The additive identity is, what's an identity? An identity is a thing where you apply the thing and you get back, there's no change, basically. So it doesn't matter what number I take. If I add 0 to it, I get back the original thing. So that is the additive identity in ordinary addition. Now later we'll talk about groups, and we have some kind of operation. It could be addition. It could be all kinds of different things. That's why I made this little circle. Sometimes we talk about a group where the operation, so groups have an operation. So groups, first off, all of these have sets to start. So it's a set, it has an operation, okay? And I'm gonna make some space for myself. So let's see how fast I can do this. Oh. Okay. So it has a set. Oh, I deleted operation somehow. Operation. Sorry. I'm learning. Operation. Meaning, so technically it's a binary operation, meaning that it takes 2 inputs and then it gives you an output. So it's very general, this thing, the group thing. And normally an abstract algebra course kind of starts from the bottom and builds up. So they start with groups, and a lot of times the focus really is on groups. And there's a bunch of other things. There's I don't want to say them yet. I'll say some of it later. But I'm going to, at some point, define what a group is. And you might be saying to yourself, well, why this definition? Why these things? And there's kind of two answers. One, we don't have to choose that definition. You know, we can remove parts of it, but then it becomes a different mathematical object. So the focus on groups is because mathematicians realize that groups are super important. And, you know, rings and fields are important, and that's why we're talking about it. There's a bunch of other things, yeah, so I'll mention about it later. But anytime you enter some area of math and someone is telling you, hey, this is the object we're going to talk about, basically what you should keep in mind, because you're going to, it's normal to ask yourself why. And just keep in mind that when they present you with that thing first, either that thing has turned out to be super important, or they're just building up. They're going to build on top of that. They want to give you this mathematical object or mathematical structure, which is it's turned out to be super important. And we know that from experience, from history. We've found that certain things are particularly important. More on that later in the specific context of groups. Now I'm getting a little abstract. Let's ground ourselves again. So recap a little bit. Fields, fields. Real numbers, rational numbers, which briefly, a rational number is like, it can be described. Actually, it means that either if you describe it as a decimal number, which just means, you know, deci is base 10. So an ordinary number, okay? So it could be 3.2, for example. This can be described as a fraction, 32 over 10, right? Any decimal number that it doesn't go on forever, can be turned into some kind of fraction like this in a fairly straightforward way. So if it was 3.24, just make it this, you know, fairly straightforward. Now, you could also have this, the 3 goes on forever, 3, 3, 3, ... And this can just be described as 10 over 3. Because there's some, not only is it a pattern that emerges in the decimal, but it's a repeating pattern. And the repeating pattern means that there's some way to describe it as a fraction of two whole numbers, two integers. And so that's sort of the definition of a rational number. Now, there are patterns you can have in the decimal that are not rational. For example, if it's a 1 and then a 0 and then 1 1 and then 0 and then 1 1 1 and then 0. So I'm just having a 1 and then then a 0, and then I'm having 2 1s and then a 0, and then 3 1s and then 0, and then 4 1s and so on. So that's a pattern that's easy to follow, but you cannot describe this as a fraction of two integers. And so this is a irrational number. Okay. And so pi, for example, so a square root of 2 is an irrational number. Square root of 5, etc. is an irrational number. Pi is definitely not a rational number. It's a transcendental number. E is a transcendental number. I'm not too clear on what the difference is between an irrational number and a transcendental number. So that's an interesting question. I need to learn that. But yeah, that's what a rational number is, right? And then we have the complex numbers with the square root of -1 and all that. That's another can of worms. But so these are fields that most people are somewhat familiar with. And again, you have plus, minus, multiplication, and division. Now, division, So we talked about the additive inverse is subtraction. So a lot of times we will not bother to write these out. We'll just say like plus and multiplication and their inverses. You see, the inverses are minus and division. So now, but you have, if you just boil it down to addition and multiplication, and if you want to include subtraction and division, you do need to then say and their inverses. You see what I'm saying? So you can decide whether or not to do that. But okay, so rings. So what's an example of a ring? Well, the integers are an example of a ring. So you're very familiar already. That's just all the whole numbers, but we also have the negative numbers, and so dot, 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 blah, 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 -3, and we include 0, of course. Those are the integers, dot, 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 0, all the positive whole numbers, yada, yada. If you don't know what integers are, you need to brush up on your prerequisites before we can have this conversation. These are, so the integers form a ring. We have addition. So it's important that there's closure, because if you have just the integers and then you add division, well, 5 divided by 4 is not an integer. So you do not have closure. So when I say you have these things, I mean with closure. So when you do these things, you don't get something that is not in the set that you started with. Okay? So an example of a ring, we have the integers. We start with a set of integers, and we define addition, subtraction, and multiplication on the integers. And that's not hard to do, and we observe that we have closure. So, this is a crash course, and there's more. You can look at technical definitions where we list out like all the things that are required and all that, and that's good to do. But in that case, we should honestly start with groups, because we kind of there's an argument that the logical thing to do is to build up from here. Groups are sort of the more general object that have the least requirements. They're more general. Okay. And so for a group, we start with a set. We define an operation, some kind of binary operation. That means it has 2 inputs and an output. It could be addition, it could be multiplication, it could be a symmetry operation, like a reflection. You're talking about a geometric object, and you're like a set, for example. We're getting concrete here. We're giving you an example of a group. The set is the configurations of a square, and we're looking at, so let's say we label the vertices of the square 1, 2, 4, 5. What the heck am I doing? I can't count, apparently. 1, 2. Let's go around like this. 3, 4. Okay, just labelings. You could do A, B, C, D. It doesn't matter. Just labelings. And we want to preserve the square, but we can move the labelings. So, for example, we could rotate everything like this, and then we would get 4, 1, 2, 3, like that, right? Does that make sense? Just rotated everything by 90 degrees. But we're not counting like something like this, okay? For whatever reason. If you want to count that stuff, that's a Lie group, that's a continuous group. I made a video on that before. You can check that out. It's complicated. But anyway. We're talking right now about discrete groups, not continuous. Okay, so this is one option. We can rotate by 90 degrees, pi over 4. Pi over 2. We can do that again, right? We can do that one more time. We'll get 3 and 4 and 1 and 2. I know this is really simple and boring, but this is a simple example of a group to start. And so that's what? 180 degrees. We can do it again. Yay. 2, 3, 4, 1. Okay. And if we do it again, we get back to where we started. So 360 degrees is basically the same as the identity of doing nothing. Equals 0 degrees. Same thing, right? So there's other labelings we could do. So like we could just switch these two, for example. Now, so there's two different groups, depending on if we allow that kind of thing. So I know this might sound like it's getting a little complicated, but basically, you notice in these rotations that we did, and if we're just doing rotations, that's called a cyclic group here. You notice that the order stayed the same. It went 1, 2, 3, 4, going around clockwise, right? Let me make sure I got the mouse. Yeah, the mouse is in the recording. Okay, so the order stays the same here with these rotations, right? If I were to say swap the 1 and the 3, or really if I just did a swapping, so I swap 1 and 2, for instance, we get 2, 1. You see the order changes, right? It gets weird. So, and actually it goes the opposite order. 1, 2, well no, and then it goes like this. So it's a little weird. So, and also that would sort of twist up the square, right? That would be weird. Like swapping 1 and 2 only doesn't make sense. We would be changing the shape, wouldn't we? That's just weird because it's like we're twisting it. Do you see what I'm saying? We'd be twisting the square because 3 and 4, that side is staying the same. And 1 went over here, so we're twisting the edge now into this kind of object. You see, so the edges are changing. So we're not allowing that. If we allowed all of that, all the possible relabelings, that would just be a permutation. We would be saying, it doesn't even matter the geometry, we're just ignoring the geometry, basically. If we allow all possible relabelings, well, we have 4 elements, right? So for the first choice, we can choose 4 possibilities, and we've taken up 1 possibilities, and then we have 3 possibilities for the next choice, 2 for the next one, 1 for the last one. So this is just permutations, and in group theory they call that, I think it's called the symmetric group, and it's just, we label it SN. It's a little confusing because in totally different contexts, S refers to a circle, so like S2 is a circle. S1 is a circle. Because the circle, we're not talking about a disk. A disk is filled in. The circle is just the outside surface, and this is one-dimensional. So S2 is actually a sphere that would be naturally embedded in 3 dimensions. And S3 would be a hypersphere, the kind of sphere you would find to be naturally embedded in 4 dimensions. So that's a little confusing because we also use SN for what we call the symmetric, I believe it's just called the symmetric group, and it's just these permutations. And this is the most general group. So anytime we study a finite group, it sort of sits inside this permutation group. So that's going to be a theorem later, but we need to define what a subgroup is. So like a subgroup sits inside a bigger group. So the biggest group here in this discussion is just where we allow all possible permutations of these labelings. So there's 4 labelings, but that allows this weird object. So why are we even talking about a square then? So then we could talk about just these rotations only. That's called a cyclic group. And or we can talk about, for example, where we flip the square. So let's say we started 1, 2, 3, 4. We can flip it in various ways. We can flip it across like this. So now think you're in 3 dimensions, because I think that's not a difficult thing for you to imagine, right? And we flip this across, right? So we end up with 4, 2, 1, 3. And or we can flip across like this, or we can flip both, 3, 4, we can flip both sides around, so this entire thing over here, and this entire thing goes over here, so we get 2, 3, 1, 4, And that's called a dihedral group if we allow those things. And don't worry if you don't understand what I'm about to say, but when we allow that kind of flipping where we're like using the third dimension to flip it over, that's like a linear transformation that has a determinant -1. And so it's a big difference if we allow that or if we just stick to the rotations, which are just determinant 1. And even if you're talking about permutations themselves, you can talk about even and odd permutations, which you can kind of think about as being a similar idea to like this determinant of +1 or -1. Anyway, that's linear algebra stuff, and don't worry if you don't understand that stuff. But point is that if we're talking about flipping around a square, and this is a very simple object, right, a square, we can basically talk about these two possible groups. There's a very obvious cyclical group of order 4 because it starts with 4 elements, and there is this thing where we add the third dimension where we can sort of flip things around, which will change the order. And if we allow that, it's called the dihedral D4, the dihedral group of order 8. This will have order 8, and let's walk through this a little bit. So when we had the rotations, we had the identity element, which was E, okay? We had 90-degree rotation. We had 180-degree rotation, 270 degrees. If we go to 360, I need to make this smaller because there's going to be 8 things here. So E, 90 degrees, 180 degrees, 270. I should have picked a smaller group for the first example because we're going to do this like multiplication table. And we're going to build it out. But let's start with the cyclical group here, which is just these rotations. And it's a subgroup of the dihedral group, which allows more. And it's a subgroup of the symmetric group, which is the full permutation group of 4 elements. So S4, we talk about the order as like the number of elements of the group. Because there was 4 possibilities times 3 possibilities times 2 times 1, that's 24. That's 24 elements in the group. So we'll have order 24. So if you're writing out all the possible elements of the group of S4, you need a multiplication table with 24 rows and columns, because when you do the multiplication table, you're going to write all the possible compositions of permutations. So like this is getting a little more detailed than I wanted to get into for this video, but like this is the identity permutation. There's no change, and there's various ways of representing permutations, which is worth studying later maybe. But like, for example, we could just swap the 4 and the 3. That's a permutation. Or we could swap the 4 and the, you could swap anything, So, and here again, we can look at if it's even or odd and think of that as a determinant, but that's getting a little more detailed than I want to get. Okay, so just looking at first at the cyclical, the rotations basically of the square. So these are going to be compositions. So, and I'm going to start with the left one and then apply the right one after. Here, I don't think it's going to matter, but sometimes the order will matter. That's a question of whether it's commutative or not, right? So anyway, so the E, that's the identity element. Sometimes it's written I, sometimes it's written as a 1, sometimes it's written as an E. I don't know why, but whatever. And that's doing nothing, right? So if we do nothing and then we do nothing again, guess what? We did nothing. And if we do nothing, again, we're starting on the left side first. If we do nothing and then we do a 90-degree rotation, well, guess what? That's a 90-degree rotation, and same for these, and yada, yada, yada. And what if we do 90 degrees first and then we do nothing? Well, like these rows and columns are super boring. Now, what if you do a 90-degree rotation followed by a 90-degree rotation? That's a 180. I almost made a mistake. That's 180. 90 and then, yeah, so you can see that this is going to be symmetric. 90 and then 270, that's going to be 360, which is E. And this will be 270, and this will be E, and this will be E, and 270 with 180 is going to be 90 degrees because it goes around 360 and then 90. And this will be 180. And so this is a group. And so you can, I don't know if I'm going to do it right now, but you could maybe as an exercise also look at the, let's say the reflections. So if I swap the 1 and the 3, that's a reflection about this axis that I am terrible at drawing straight. You reflect about that axis. If you're switching this left side with the right side, that's a reflection along this axis. So you can reflect along there, you can reflect along here, you can reflect around here, you can reflect around here. Those are 4 options. 1, 2, 3, 4 different options. And so let's say, like, you just pick some label, like Rx, for instance, we'll say is reflection about here. So it will go from 1, 2, 3, 4. It will become, you kind of have to be like creative and flexible. You can make up all kinds of labels and all this kind of stuff. But reflecting about there will be 4, 3, 1, 2, right? So if, okay, doing nothing, the identity, and then this thing will be Rx. And then, so if we did 90 degrees first and then 1, 2, you can work it out. So 1, 2, 3, 4. We do 90 degrees, we get 4, 1, 2, 3. Then we reflect about the x-axis, we get 3, 2, 4, 1. Now you need to come up with some kind of labeling for this. What is this? 1, 2. It's actually just going in the opposite direction now. But, you know, you could call this A or something, right? And then fill in this whole multiplication table with 8 elements. Maybe I'll put it on the screen maybe if I edit this video. I don't know if I'm going to edit it. But anyway, so we showed this cyclical group, which is symmetric. It's commutative. We have this fancy name for that. We call it abelian. It's named after a mathematician named Abel, I think is the name. Abel. Anyway, abelian. So just fancy language to say it's commutative. So there's this like, so it doesn't matter about the order here, the way that we've done this, right? For the cyclical group here. Okay, so that's an example of a group. So what were the minimum requirements? We started with a set, we had an operation. Now here, so this is, I remember this was super confusing when I learned group theory in high school. I was sort of, yeah, most people don't learn that in high school, but I was super confused because, so what is the operation here? The operation is just composition. Okay, so the most general operation we just call composition, and you can always just call some operation composition and label it with this dot. So like, for example, there, you could have 90 degrees dot reflection about the x-axis, for example. Okay, so yeah, this large dot thing is just what we'll call composition. So what is the operation in this example of this group that I gave you? It is composition. You can probably always get away with just saying that and then I guess the other thing that's confusing is there's like this confusion between objects and operations, because here the objects are also operations, but that's not always the case. So let's use an example where our binary operation is ordinary multiplication. Okay, let's give an example of this because I want to give you some examples. And let's choose 1, I'll give myself some space in case I need it. So 1, which is the identity. Now we're choosing, because we're talking about ordinary multiplication, you know, the number 1 is, we could write it as E, but we could just write it as the number 1, right? And let's get fancy and choose I. So our set, I'm going to add to the set. I want to demonstrate something, but we're definitely going to have 1. So you need an identity. So this is a requirement of a group. You start. I should have given myself more space. You need an identity, which is under the, what kind of identity? Like, is it additive identity? Is it multiplicative identity, right? Multiplicative identity normally is 1. The additive identity is normally 0, right? These are the things that you apply to get back the thing that you started with. Well, it's an identity under whatever the binary operation is. So that could be whatever. So it's unclear, but it has an identity. A group needs an identity. So we start with a set. We define an operation. We have an identity. The other thing is that, I'll just say more, like maybe finish the requirements for now. We have inverses. Every element has an inverse. Okay. So in the example here, so an inverse element means that, let's say you have an element A, and the inverse we always write like this. This will always equal the identity element. So that's the definition of an inverse. It undoes the element. So I'll have to be technical with my language. The inverse is an element of the set of the group that, when applied to the element that we're talking about, under the operation defined with the group, gives you the identity. I know there was a lot of because we need whatever, there's some operation happening. So when we apply this operation that we've defined, this inverse element applied to the original element will give us the identity. And it doesn't matter about the order. It will not matter about the order. We get back the identity. That was a big mouthful, but it just undoes the thing and you get back the identity. And looking here, so the inverse element of 90 degrees is going to be 270. If we compose these, 90 degrees composed with 270 degrees is going to be 360, which is the identity here. The inverse element of 180 is 180. It can be its own inverse, there's no problem. And the inverse of 270 is 90. Okay? So for reflection about the x-axis, the inverse is itself. You do the reflection twice, you get back where you started from. Same with every reflection, right? Every reflection is its own inverse, yeah. Okay. So we require identity, inverse. Also, what's required is associativity. And hopefully you understand that. If not, look it up. They're all associative. So there's really these. So we define the group with two things, the set and an operation. That defines our group. But we need to check that it has three properties: identity, inverse, and associativity, and also closure. Closure is the fourth one. These four properties. Yeah. Identity, inverse, closure, and associativity. Okay. All right, so now we're doing our operation is ordinary multiplication. And I'm choosing some set. I'll start with 1. So that's a group. 1 times 1. We can write out the multiplication table. I think it's also called a Cayley diagram. There's this mathematician Cayley who contributed greatly to group theory. So 1 times 1 is 1. That's it. We could also label it with E. We could label it really with whatever we wanted, right? A big I is sometimes used. And this is sometimes called a trivial group. It's just the identity. And you need to define the operation. In this case, it's ordinary multiplication. So group theory is confusing to learn because when you're reading about it, when you're working with a textbook or whatever, sometimes the times symbol will be used for the operation. We could have used that up here too. We're free to use that if we want to. Sometimes the plus symbol is used. Why not? 90 plus 270, that also works, right? It's just a labeling, okay? And sometimes this symbol is used, and sometimes no symbol is used. So let's say, yeah, for our label, just like ordinary multiplication. If we have we have the E as the identity element, and then we have 3 other elements in the group. We might label E composed with B. We just write EB. B composed with C, BC. Sometimes just nothing is written. So you have, I don't know how to write nothing. I'll leave a little space for it. Sometimes you see a times symbol, sometimes a plus symbol, sometimes this little circle that is meant to sort of, you say composition, basically. But all of them are composition. So that's sort of the safe road. It's always, you can always, pretty much always refer to it as composition. But if your operation is just multiplication, or especially if your operation is just addition, you sound a little silly referring to things as being composed, like the composition of the group elements. They're just being added, so you kind of fall back on using that symbol and using that language as well. So let's use I, where of course I is the square root of -1. Don't worry too much. So if you don't know about imaginary numbers and the square root of 1, for now just consider I to be a label. And so instead of the trivial group, which all groups must have the identity, so and again, we can just label it however we want, just exposing you to the normal things that you're going to see. So 1 and I, let's start with that and see if we have closure. We have to have closure on our set. And if there's anything missing, then we need to add it to our set. So 1 and I. So what will happen? Well, 1 times 1 is 1. 1 times I is I. I times 1 is 1. I times I is -1. So this is not a group because we don't have closure. -1 is not yet defined. It's not part of the set that we've used to define our group. So we need to add it. So let's add -1 to our multiplication table. Now we get -1 times 1 is -1. -1, now we have -I. So we're going to need to add that as well. But let's finish this part of the table. -1. We have -I. -1 times -1 is 1. So that's another, you can make a group under multiplication. That's the lingo. We say a group under addition or group under multiplication, etc. So you could make a group under multiplication just with 1 and -1. What's the multiplication table? A very simple group. 1 times 1 is 1. 1 times -1 is -1. -1. -1 times -1 is 1. That's a group. And there's 2 elements in the group. So we say it's of order 2. Actually, pretty sure there's only one group of order 2. And that's this multiplication table. So you can relabel everything. You could say A and B. A, B. And A times A, in this case, is A. A times B is B. B times A is B. B times B is A. Right? And so if you were given just this multiplication table, you might be asked, what is the identity element here? Is it A or B? Well, you have to work it out. B times B is A, so that's definitely not the identity. Because the identity, anything composed with the identity should be the thing. So it should be B here. And they might, this is just a labeling. They could give it to you the other way. They could give it, first off, with B and then A, okay, and filled in the same way. A and A composed with A. Sorry, B composed with A. A is the identity here, so B, okay. They could give you that. They could also just relabel everything with the same structure. So here, B composed with B is B, and then B with A. I'm getting confused, but here now B is the identity. So I'm gonna make my life simpler and use that information. A with A. So let's say I tried to do this. A with A is A. Well, what's the identity element? We see B is an identity element. That's okay. But what about inverses? See, inverses, A has to have an inverse. A composed with B is A. So we see that B is the identity here in this labeling, right? I'm getting a little abstract. I know this is a little confusing, but you need to, right? It's not that confusing if you boil it down. You got to work with it. We started with this multiplication table. I've told you that we can just relabel things. Now I labeled this in exactly the same structure, but I could just relabel it some other way, right? And here now B is the identity because we check each combination. B composed with B is B, so you get back the thing that you started with. B composed with A. Oh wait. Excuse me. Huh? I messed it up. I don't know. But there's definitely this is not going to work. You cannot have both an identity and you cannot have both an identity and where every element has an inverse in here. So check that out. So this does not work as a group, as a multiplication table. You only have this, and again, here we could switch the labelings. I'll just write that up here. It doesn't matter A, B, right? So we could have B, A, but we're going to need the same kind of structure. B, A. So it's going to be, for example, here, B is the identity, B, A, A is B. Okay, this is a valid group. And now B is the identity. B composed, so let's do left-handed and right-handed separately. I know this is like overkill, but B composed with B is B. You get back the thing. B composed with A is A. You get back the thing. Now, right-handed. The thing composed with B, you get back the thing itself here. And the thing A composed with B, you still get back the thing, A. So B is the identity element here. Identity element is B. Okay. And it will be its own inverse. B times B is B, which means it's its own inverse. Okay. What about the inverse element of A? So the question is, what is the element that composed with A gives you the identity? The identity is B. That's here. And we see that A composed with A is B. So A is its own inverse. And it works both ways, whether you compose it, talk about it from the left or from the right. That situation is sort of commutative. So A is its own inverse. So we have every element of this group has an inverse, and there's an identity element. And you can work out if there's associativity, that would be like checking the possibilities. These kinds of possibilities that this needs to equal A, right, where we would just move the parentheses. Now, in this case, the group is so small, you could do that for every possible composition that's there, and that proves it, that it's associative. But there'll be other examples where you need to prove associativity. So again, identity inverse, this is kind of what I'm focused on. And the last thing, associativity, sometimes comes easily because usually most things you multiply them, they're associative, but you need to think about it. You might need to prove it. And personally, I'm thinking about closure the whole way through. Like this becomes automatic closure. Yeah, so those 4 requirements, right? So this was a relabeling, and we indicated that doesn't matter about the labels, we can prove that this is a group. It's just a multiplication table. So it's even, so this is super general, because what is the operation here? If I just have a table, a multiplication table, I'm calling it a multiplication table, but it doesn't, but I shouldn't even use the word multiplication. It's a composition diagram. We call it a Cayley diagram. But the operation here is just composition. I can get really general. I'm not even, these are just labels. These are elements. My set here is A, B. That's it. My operation is composition. So I say it's an operation defined by this multiplication table. Or this composition table. That's the definition of the operation. And then I say, prove this is a group. Now, with this example, notice this was different because we had A's going through, there's like this structure of A's, right? Whereas in this one, it was the diagonals, B, A, look how messy this is all getting. A, B, C, like these had the same structure, these two. And these two are both groups. But this one is not a group. And so maybe as an exercise, like, try to prove, either find that there's no identity, check both in B and A and see that there's no identity, or show that one of the elements doesn't have an inverse. I think A doesn't have an inverse. Okay, so these are very simple examples, and you can see that this is kind of getting confusing and messy, right? And we're talking about, it's abstract. I'm talking about labelings and what is the operation. It's just composition defined by this table. So it's abstract. But for motivation, it was this. And so of order 2, there's only, so we say up to isomorphism. So what do I mean by up to isomorphism? Isomorphism is this fancy word that iso means same, and morph means form or shape. So no matter what labelings I choose, right, with A's and B's, or you can use sigmas and deltas and whatever you want. You can actually, sometimes people will literally use like shapes in the multiplication table. It doesn't matter what your labelings are. The structure is the same. We have here a major, we have 2 diagonals. That's it. And so up to isomorphism, there is only one group of order 2. The up to isomorphism means regardless of your labeling, there's just one structure possible of order 2, where we have 2 elements. Now, same thing for order 1. There's just the trivial group of order 1. Okay? Now here we saw, getting back to this one with i's and negative ones, we saw that we don't have closure here because we have now a negative I. And sometimes forget that you're talking about numbers and just think of labelings. You might have thought for a moment, well, is it okay to have negative I because we have I here as an element? So is negative I okay? That's a different label. You can always go back to thinking these are just labels. So negative I times 1 is negative I, and that's going to be up here as well. Negative I times I is negative I squared, which is positive 1. That's over here. This situation is commutative because complex multiplication is commutative. So that creates like this line of symmetry going down the middle, where these are sort of symmetric across here. Does that make sense? So that's what a commutative or abelian group looks like. So negative I times negative 1 is positive I. And again, same here. Then we have negative I times negative I. The negatives cancel out, so we get I squared, which is negative 1. And I regret having this thing here. Remove that. And we'll fill it in. Oh, that did a lot. Okay. And this will be I squared, which is negative 1. So now we have closure. And this is indeed a group. So you can see that we have structure, and throughout this discussion, there are like a sort of a theme here is symmetry. Groups are really all about symmetry, and they're really the study of reversible operations, basically, because we have this inverse. So everything is reversible. So in full generality, we're just studying sets with reversible operations. And so it's very, very general, and it's very, very abstract. And then the first sort of obvious project of group theory is to classify all the finite groups. And that's a huge endeavor, which has maybe kind of been done, but it's like 20,000 pages or something, and they're continuing to work on it. But there's lots of important groups. I will probably make another video where I talk about lots of different important groups. And then of particular importance to me is these sort of continuous groups. They're really called Lie groups. And for example, if we made this continuous, so we just have the rotations in 2 dimensions, that forms a Lie group. Check my previous video about that. Here too, kind of a similar idea. You could also be talking about where you not only rotate, but you mirror everything. So you have a 2D image and you just flip it, you mirror it. And from a linear algebra standpoint, we call that that would be a transformation of determinant -1. So the determinants, I'll talk about it later at some point, but as a transformation, if the determinant is 1, this means that it's distance preserving. So all rotations are distance preserving. Nothing is getting scaled. So rotations are determinant 1. And determinant -1 basically means that something's getting mirrored, getting reflected or flipped. But I want to be precise, reflected once. If you reflect something twice, you get back to determinant 1. Or if you reflect an even number of times, you get back to determinant 1. And in fact, so that's a very interesting thing to me from studying group theory. All rotations can be expressed as compositions of reflections. So that's an interesting thing to think about. If you compose 2 reflections, imagine you have some your good old coordinate axes, and you we're going to only do reflections for now through the origin. You have some reflection here, and you have some reflection here. Maybe play around with this, with some drawings and stuff, and see if you compose 2 reflections where they're going through the origin, this will always give you a rotation. So that's kind of interesting stuff to think about. But I'm very interested in continuous groups, which are basically Lie groups. More or less, maybe not technically, but basically that's the idea, and that's of extreme interest. But normally in group theory, the focus first is on finite groups, and there's an enormous amount of study of this. And I want to talk a little bit about the importance of it, because I think it can seem very abstract and just kind of like, yeah, okay, I get it, it's important, but is it really that important? And then I want to get back to rings and fields and then wrap up the video. And I'm not going to go into as much depth about rings and fields. But again, like groups are super important. Like the first object that you talk about in abstract algebra is super, super important. And So it's ultimately, because it's about these reversible operations, there's always symmetry. If an operation is reversible, you can think of that as a symmetry, right? You can do it one way or you can do it the other way. And when we study sort of spaces in general, one way to define a space in a way is to look at the possible symmetries. And so this was, in particular, there's a mathematician named Klein, and he has this project called this Erlangen project. Erlangen, and also Sophus Lee, who the Lie algebra, or Lie, the Lie algebra, that's another very closely related thing. But the Lie groups, named after Sophus Lee. Sophus Lee was a Norwegian who was a friend of Klein. And Klein realized that, was studying, in particular, say, projective geometry and hyperbolic geometry, these other non-Euclidean geometries. And basically realized that you can describe these complicated, more general geometries through looking at describing their symmetries, describing their groups. And so that non-Euclidean geometry is super important. It's hyperbolic geometry is sort of the stage where social relativity, special relativity is played out. That's in the world of hyperbolic geometry. It's kind of fancy, but it's not that big of a deal. Instead of a circle, we talk about hyperbolas, and roughly speaking, there's a lot of fancy technical stuff we can get into, but so this hyperbolic geometry turns out to be super, super important and more general than our Euclidean geometry that we're used to, like our flat geometry, like you learn about in school. And so these groups can be used to describe these spaces. So group theory and Lie theory turns out to be super important for describing spaces and, of course, symmetry. So we can describe different very abstract spaces by studying their symmetries, the possible symmetries within that space. Okay. So super, super important. Now I want to talk about, let's see. So I gave you an example of rings, and rings, we start with this. What often happens is we take our binary element, at least when we're moving up to a ring. Yeah, our binary element is usually it's addition, and it's commutative. So we start with a commutative group that's called an abelian group, where the operation is defined as addition, and we start with that, and then we equip it. Of course, we get minus for free because the fact that it's a group means that the every element has an inverse, and so if we defined our operation as addition, then if we properly defined everything, we have closure, and every element has an inverse, we'll get subtraction for free. So we start with an abelian group where the operation is defined as addition, and then we basically add on top of it multiplication. So this is super rough, loose, like very much a crash course in this overall structure here. But basically you take this abelian group where you have addition defined, and then you add onto it, you tack onto it multiplication, and then you get a ring. And then if on top of there you also have division, in other words, the multiplication is invertible, then you get a field, roughly speaking. And there's other fancy ways to do definitions, but I think everything I said is basically correct. And I've given you these examples of fields and rings. And so again, like we talk about rational numbers, or we talk about real numbers, or we talk about rational numbers. And we're quite familiar with that. But to get to this definition, we had to start with groups. And so it's rather abstract. Then we go to rings. And ring theory is big and important as well. In particular, matrix algebra is sort of, they form rings often, so that's kind of important. And there's one more thing I wanted to say, but I kind of forget. I'll have to be another video, I guess. There's something important I wanted to say. But, yeah, I think that's it. Oh yeah, so I just wanted to contrast it with a vector space. That was it. Because this might, let's see, if we define, so those who have watched my video on a vector space or who know what a vector space is, the thing was we had scalar multiplication. So if we start with a group and then we define the operation as addition, we haven't defined any scalar multiplication. So scalar multiplication is nowhere in this discussion yet. And that's the key thing that separates a vector space from all of this. But basically, I'm not an expert on this stuff, but if you're talking about multiplying matrices, you have addition, you have multiplication, and you also have scalar multiplication. So that's an algebra, but it's also a ring. Yeah. So at some point we'll have to discuss what an algebra is and what kinds of algebras there are. And that's interesting stuff, and that gets into deeper mathematics. But I think that having this general overview of group theory is kind of good for anybody interested in STEM fields. Like if you're really serious about programming, it's not really necessary for if you're programming games or just programming in general. Most programmers don't. I mean, if you studied computer science in college and got a degree, probably you studied abstract algebra. You probably took a course and learned about groups, and you learned definitely you hopefully studied linear algebra and you learned about vector spaces and matrices and all that. But at the end of the day, honestly, for programming, usually this is not super important unless you're getting it really, really deep into computer science and that kind of stuff. But I think it's great to have this overall sort of bird's eye view of certain areas of mathematics, so that if somebody talks about a field, oh, okay, you have some intuition of what that is. Same with rings and groups. And I think groups in particular I'll probably make some more videos where we can practice more groups, study more groups. Certain groups are really interesting, and I kind of I didn't say it explicitly, but like this cyclic group and dihedral group that I was talking about, you can see how it kind of fits into this stuff I was talking about with the Lie algebra or Lie group. So these finite groups somehow sort of fit inside of these Lie groups sometimes, and I find that really interesting. But that's it for now. So thanks. Take it easy. Have a good day. Bye.